Today it is an important day because this is the first time we're going to have an Einstein Lecture. So we're all waiting for Einstein Lecture. And Hans Albert Einstein Award is acknowledge the significant contribution to the engineering profession in the areas of erosion control, sedimentation, and waterways development, either in teaching, research, planning, design, or management. So this year's Hans Albert Einstein Awards goes to Stanford Gibson. And most people know him, and we were using high-class sediment model. And his outstanding contributions to numerical modeling of sediment transport is well known worldwide.
Thank you to distinguished members of the council. And the Einstein Award is particularly meaningful to me because I live sediment. I had a friend come by my office a couple of years ago and say, you know, you have lots of interests. I actually have 3 master's degrees as well as my PhD, and most of them are in engineering. And he said, I'm surprised you haven't moved on from sediment yet. I'm surprised that this has held your attention for so long. And I sat back in my chair and I said, you know, maybe when I figure it out, I'll move on. But we're engineers. We solve difficult problems, and there's nothing like sediment. And so Randall Munroe, he wrote a webcomic for years until the New York Times hired him to write kind of a visual science explainer column. Many people sent me this when it came up on the New York Times a few months ago. Munroe said, I'm going to rank the disciplines of physics in order of difficulty. And I'm going to start with Newton's laws, move to special relativity, and then we get really hard, like quantum mechanics and general relativity. But if you really, really want to tackle the hard problems, you need to deal with sand. Sediment transport, particulate transport, is an unsolved problem. It's an unsolved problem. We don't have an open form equation that can do that. But we're engineers. And around the world, sediment transport causes civil works problems and environmental problems. And just because there's not a scientific solution to those problems doesn't mean that we're not going to take a shot. And that's really what my career has been about, is embracing the uncertainty around sediment transport to try to reduce the uncertainty for civil works and environmental projects. But there's another reason. It's not just because it's hard. There's another reason that I love sediment transport. And that's because I'm fundamentally a generalist, which is strange to get a specialist award, but here's the secret about sediment transport. To be a specialist, you have to be a generalist. We saw a diagram like this in the excellent preliminary talk yesterday, and this is the way I think about the world. I think about engineering problems on multiple spatial and temporal scales. This is not unique to me, but I use this heuristic in my opening talk for my sediment transport class because, as Dr. Dewan said, I'm primarily known for this. I'm primarily known for adding mobile bed sediment transport to HEC RAS. Now, many of you do what I like to call blue water RAS. You put a flow in the top, and then kind of adorably, the bathymetry doesn't change. And so you just put a flow in, and the water surface happens. But you might not know that you could also put a sediment flux in the top, and then things get weird, because you end up with a sediment surplus or a sediment deficit, and you end up depositing, eroding, which means we have to change the bathymetry. And that's what we do in RAS. But in order for you to understand these scales, the like 10 to the 1, 10 to the 2 spatial and temporal scales that we care about, you really have to interact with these smaller and larger scales. And this is part of the brilliance of Hans Albert Einstein, is Hans Albert Einstein worked at all of these scales. We know Hans Albert Einstein for his great monograph on sediment transport and mixed load transport, or with the really thorny integral in the middle. This was decades before its time. But the reason he could do that great work is because it emerged out of really high quality experiments, and then he applied it in the field. So I am a federal practitioner. I've worked on most of America's big rivers. And it seems like I can't work on any river in America without getting to the point where I learned that Hans Albert Einstein was there and made a contribution. And this is a picture from Rob Edema's great biography on him with Einstein on the Missouri River, which we'll talk about. So even though I'm known for that reach and river scale, I thought I'd try to, I have a rule at dinner parties. I will only talk about my job for 2 minutes, because while I love sediment transport, I can't imagine that anyone else could be interested in that, and they've given me 30. So I've decided to talk about the things I think are interesting in my career rather than important, and especially the ones that have fun visuals. So we're going to walk through the spatial and temporal scales of sediment transport, and we're going to start with the experimental scale. Everything about what I do in sediment transport emerges from, can I help you solve problems with software? This is our governing equation. Now, Chester Watson at Colorado State used to like to say there's no way to lose a crowd faster than throwing up the backward sixes, right? They're the gang sign of engineering. And I mean, I'm at an engineering conference, right? But I promise this is the only equation I'm going to talk about. And actually, I shouldn't talk about this because this isn't my equation. This form of the equation comes right out of Weeming's textbook. We are very much in the Wu tradition. And so if you have questions about what the particle velocity is doing in the temporal term, ask him, because it's better there. It's a beautiful equation. It's a gorgeous constituent transport equation, except there are these two empirical terms, the particle velocity, or the advection coefficient, and the diffusion coefficient. And we kind of can think about, how does sediment transport move? Like, what's its velocity and how does it diffuse? If you think about suspended or wash load, that's kind of like any other solute. But how does this work for bed load? That's a question I always had. And when I had a question about the equations, it usually drove me to the lab. And so this is my favorite lab study we did. You've got sand on the bottom and gravel at the top at about the same shear stress. And we're going to put in pulses of material, and the only thing that's going to differ over time is the color. We're going to put in red first, and then purple, and then yellow, and then green, and then blue. And you've got 30 seconds to develop a hypothesis. Would you expect the gravel to have a higher particle velocity, or the sand? And would you expect the gravel to diffuse more, or the sand? Well, I can tell you that if you develop the wrong hypothesis, you're in good company, because I also developed the wrong hypothesis. I thought that the sand would move faster and mix more. But what you're seeing is that the arrival time of the later particles, the yellows and the blues, they get there faster with the gravel, whereas the sand moves in packets. It moves in these waves. And so the sand velocity, even though the sand is more mobile, is limited by the mobility of the structure of the bed form. And so you get more mixing, and once a gravel particle starts to move, it can move indefinitely. Once a sand particle starts to move, it can only move one bed form. And so after the experiment, we took samples every 0.3 meters, or every foot for people from this country, of a 70-foot or 50-meter flume. And we developed color distributions. And those color distributions, they're PDFs, they're probability distribution functions, which means we can take the first and second moment in order to get particle velocity and diffusion. Now, if you're not a sediment person, particle velocity is on the y-axis on the top, and diffusion is on the y-axis on the bottom, and we have the Shields number, the magical sediment transport number, on the bottom. But if you're not a sediment transport person, let's just say you hold shear stress constant. The larger particles are going to be on the left, and the finer particles are going to be on the right. So what do we have? The coarser particles move faster. The less mobile particles move faster. I love sediment transport. Also, the coarser particles diffuse more because they aren't regulated by those bed forms. Okay, the cross-section scale. The cross-section scale has been the bane of my existence because I develop a one-dimensional sediment transport model, which means that once I deposit or erode sediment in a cross-section, I have to deform the cross-section. but it's a one-dimensional model, but the deformation is rarely one-dimensional. And so one of the things we did is we partnered with Eddie Lingadoon over here at ARS and brought their BSTEM model, which is a bank failure and toe erosion model, into RAS, so that not only can RAS erode and deposit vertically, but we can do bank failure analysis within the model in real time. And then the other cross-section scale thing that I'm working on is the bottleneck of one-dimensional sediment transport is how you realize deposition in the overbanks. And right now in RAS, we have a Goldilocks problem. You can choose a method that gives you too much deposition or a method that gives you not enough. And I think we've nailed this. In version 6.6, we're going to have 3 new methods that are going to realize the floodplain deposition. But let me tell you about my favorite cross-section scale problem. So this is RAS. On the right here is the RAS that you all know and love. I like to call this classic RAS. Over there on the left, this is RAS 2025. I mentioned this in the panel discussion, but we are rewriting RAS from scratch. It's time. And this is RAS 2025. We are going to release an alpha version of this later this year, and you're going to get to play with it. Do you notice those nice linear rectangular cells? Yeah, those were really easy to make. Are you looking forward to that? If you're not, you are not a RAS user. It's going to be fantastic. You're going to love it. But whether you're doing 2D modeling or 1D modeling, the bottleneck question for sediment transport is the flux boundary question. The cross-section we care about is the upstream cross-section. What's coming in at that upstream cross-section? Now, many of us live in the United States of America, which means that we have one of the greatest scientific organizations at our disposal. The USGS goes out and measures these. And then they give us plots that look like this. And we need to fit a line through the flow load data cloud. We call this the data cloud. This was the cloud before the cloud was the cloud. Early in my career, I made about every statistical mistake you could make for highly scattered data in log space. For 10 years, I made about 8 different mistakes every time. And then when I figured out how to do statistics on this stuff, I talked to other people and realized they were making the same mistakes. We all made the same mistakes. And so what we did is in RAS, we developed a sediment data analysis tool. And what it does, first of all, is it goes directly to the USGS, downloads those data, cleans them, averages replicates, those gets flows where they're, that's about 4 days of work in order to just get your data clean. It does that in about 35 seconds. And then it applies a number of different statistical best practices so that you can fit your rating curve through these data. And so it'll go and add the bias correction, which if you don't know what that is, it's so right, but it's really important. And then it will also stratify by time and do a number of other statistical analyses. But the most important thing is that a log linear fit to these data is usually inappropriate. The problem is that the low flows drive the regression. Basically, you're getting a very bad answer in the morphologically important flows that you care about. And so what we did is we collaborated with a statistician at UC Davis in order to develop a continuous piecewise linear model and not only apply the piecewise linear continuous model, but it also goes in and finds the optimal inflection point. And now that we've been doing this a while, it's pretty fun because we get different shapes, right? These can be convex and it can be concave, and there are morphological reasons for that, which we have a paper coming out on, and you'll have to wait for that. Because the story's not over. This gets more interesting. Not only do we need a boundary flux at our sediment transport model, but RAS is a multi-grain model. That sounds like something you might eat for breakfast to stay regular. What that means is that we just don't need a flux. We need flux by grain class. We need to know how much medium sand you have, how much fine sand you have, how much coarse silt you have. That's a data-hungry model. Now, the USGS, they actually developed that data for some of their samples. And so, same thing. We'll just go to the USGS API and download those data. If I had more time, if this was a teaching environment, I would ask you, and I've done this in interview questions, incidentally. If you come work for the Corps and I'm on your interview board, you're going to get a heads up. I'd ask you, well, what do you expect? As flow increases, would you expect the gradation of the load, of the suspended load, to increase, get coarser, or decrease, get finer? Well, here's a classic case. These are the geotech curves over here. So if you speak geotech, that'll make sense to you. But over here, we have the flow on the x-axis and the D85, the 85th percentile particle size on the y-axis. So you can see that this is classic. This is a supply-limited condition. So as flow increases, you recruit coarser grain classes and things get coarser, which would be my dominant hypothesis. But I wouldn't put this in the Einstein Lecture if that was the only thing going on. This is the Eel River in Northern California. The Eel River is not supply limited. It is transport limited. It has all the fine sediment that it wants, even though it's a gravel bed river. And as flow increases, the gradation decreases. Why is that? When I'm on PhD committees, I tell people, they always come and ask, just like I did with Fabian, what are you going to ask? And I always tell them, I'm not going to tell you what I'm going to ask, but I'll tell you that no matter what I ask, the first thing you want to think is sediment transport is nonlinear. How could that answer this question? And that's what's going on here, is that because sediment transport is nonlinear, sure, coarser grain classes are being entrained, but the finer grain classes, the capacity is growing faster. And so as long as there's supply, you're going to find. And so this has been one of the great obsessions of my career. We did have a paper where we looked at 84 gauges. And basically, most rivers are supply limited because you get that coarsening condition in about 2/3 to 75% of rivers. But that was a small data set. We are doing a big data study right now on about 2,500 gauges. And so we'll kind of see how that goes. All right, now for the scale that I know something about. When Jennifer asked me to give this talk, I said, well, what should I talk about? And she said, well, maybe tell people why you won the award. And I thought, okay, that makes sense. And then I was running the next day and I said, I wasn't in the room. I don't know why I won the award. I'm going to guess it's because by putting sediment transport and RAS with 140,000 users, we've made sediment transport analysis available to more people than have ever had it available. That's my guess. But that's actually a pretty small part of what I do, because I'm also a practitioner. And so a talk like this gives you the chance to reflect. These are the models that I have built in my career. A few of them are blue, those are adorable, but most of them are brown. The circles are sediment transport mobile bed models. We got some reservoir models up there, some non-Newtonian debris flow models up there. There's one sediment and ice model, which I cut from the talk, but it's so cool if you want to talk about it sometime. We've done this modeling all over the world, and even sometimes not in the world, because if you go and look at some of my example data sets, and if you are a Tolkien nerd, you will notice that they were actually based on Middle Earth rivers. But I have time to talk to you about like 2 or 3 of these. So let me actually go to reservoirs, because reservoirs are the 800-pound gorilla in the sediment room. When Hans Albert Einstein was doing his work, we were just building reservoirs. Now we're on the other side of that. And my friend John Shelley of the Kansas City district likes to say, all reservoirs have a 100% depositional failure mode. It's just a question of time. And the clock is ticking. And so early on, when we kind of got involved in this, we thought, first of all, is a one-dimensional sediment transport model even an appropriate tool to evaluate something like reservoir sustainability operations, flushing or routing? We went to Nebraska, me and Paul Boyd, the Niobrara River, which Rollin has some very early work on. The Niobrara River drains the sandhills of Nebraska. If you build a dam on a river that drains the sandhills of Nebraska, it is going to fill with sediment. It did in about 5 years. And so this is my friend Paul Boyd. And Paul Boyd is fantastic, but he does not walk on water. Here we're taking reservoir sediment samples, and we did not need a boat. That's how full of sediment this is. And so what we did, and you're going to watch a time lapse of the drawdown flush looking up into the reservoir. What we did is we just went out and we instrumented this. We turned it into a prototype laboratory, and we measured the bathymetry before and after several times upstream and downstream. And then the USGS came in and they set up downstream and took suspended sediment samples downstream of this flush to answer the question, hey, how's a 1D model gonna do in these kind of conditions? And so you're gonna see, we're going to speed things up now, but this is all still the first day. You're going to see a capture over here. Looks like Weeming's model of DL breach, because it's basically going to breach this levee and push upstream. What happens now is a race. You've got a race. I'm trying to make sediment transport dramatic. You've got a race between these 2 channels, and which one's going to deepen first to capture the other. It's really cool. Now we get a Nebraska sunset and sunrise, and now you will see some researchers of questionable wisdom running around and taking some samples. We won't tell the core safety people who those are. And so we modeled this in RAS. And the circles are the observed downstream suspended sediment. The dark line is our simulation. And we actually did pretty good. The mass balance was pretty good. But we don't end there. What we're finding in the Willamette Valley, if anyone's following the releases in the lawsuits in the Willamette Valley, so what could we do? Well, what we did is we added sediment transport variables to the operational rules in RAS. Now, if you're a RAS user and don't use operational rules, you are missing out. What they do is you can actually operate the gates automatically based on anything that RAS computes. And so by adding sediment transport variables to the operational rules, what I said is, hey, if we have a downstream constraint that our communities or resource agencies give us, let's operate for it. And so I told RAS, hey, I don't ever want to go above 30,000 milligrams per liter downstream. And so what RAS did is operated the gates to maintain that downstream TMDL. And then you can just look at the gate operations and see what would give you that downstream TMDL. Is there uncertainty on that answer? There sure is. But does it give us a starting point to negotiate with communities and resource agencies while we try to have long-term sustainable reservoir management? It does. Now, the highest profile work we've done has been on the Mekong. We developed a routing model for the Mekong with the Ministry of Mines there, and we developed a routing regime that with 1 week annually would reduce their deposition over the life of the dam by 50%. And then long-term flushing is called dam removal. Chris Nygaard and I did a dam removal model in one-dimensional RAS. We got to calibrate it to a drawdown event on the Snake River. And these are bigger, more controversial projects, but what we've demonstrated is 1D sediment transport models actually, well applied, actually can answer some of our most difficult sediment problems. Over the last few years, we've been trying to simulate higher concentration events. You're civil engineers. Most of you have probably seen the video of the Brumadinho failure in Brazil. This is the second mine tailing failure in Brazil in a couple of years. There were 300 casualties from this event. And what you can see from this event is that is not water. If you try to simulate this with blue water RAS, you're gonna get a wrong answer. And so collaborating with a number of people, including some Brazilian collaborators and our lab, ERDIC, we added non-Newtonian physics to RAS in order to simulate these high concentration transport. And so on Brumadinho, we were within 2% of the arrival time once we added the non-Newtonian physics. And this is really instrumental to our response to post-wildfire in the West, because the Santa Barbara events in the West essentially had 80% solids by volume. If you have a flow that's 80% solids by volume, you cannot use Newtonian physics. And so we were able to turn around a model of that and in enough time to help the community plan for the next rain season. All right, the river scale. The river scale is interesting because this is where one dimension really still matters. If you're building a model that's over 500 kilometers, which we've done on the Mississippi, the Madeira, and the Missouri, then one dimension really matters. And so this is the Missouri River model that I developed with John Shelley. He went on to develop an 800 kilometer version of this. And the issue is that there's a lot of scour on the Missouri River. The remarkable thing about this model is we were able to calibrate it both to an interflood period where there's scour because of local mining and erosion during a flood. We're talking about 800 cross sections over the course of decades. This is a pretty robust model, and it shows kind of what you can do with 1D mobile bed sediment modeling over large temporal and spatial scales. We also got us asking the geomorphology question of why. Why is it eroding on those scales? Why is it eroding more during the flood? That leads to another one of my big questions I've had in my career is how do rivers respond to disturbance? Most of us assume that the river stays the same. The river never stays the same. And so what we found is that in that interflood period, the bed change scaled to the gravel mining, both in magnitude and location, scaled to the gravel mining that was happening. But during the flood, the erosion scaled to the floodplain deposition. There's enough deposition on the overbanks so that the mass balance essentially was negative, which causes the erosion. Which leads us finally to the geology scale. This is the San Rafael waterfall in Ecuador. or at least it was the San Rafael waterfall in Ecuador. About a month before COVID, which is why if you haven't heard of this, you haven't heard of this, because it is a first time in the Anthropocene type event. A water pathway formed underneath the lava dam and captured the whole river, causing the lava dam eventually to collapse, pushing a 140 meter nick point upstream. Over the course of the next few years, that erosion continued upstream. It eroded so far it has eroded 500 million tons of sediment. Just to give you some context for that, the SRS, the sediment retention structure downstream of Mount St. Helens, holds half of that. The annual load of the Mississippi is 500,000 tons per year. That is the annual load of the Mississippi eroding out of 13 kilometers in 4 years. Now, this headcut has pushed 13 kilometers upstream. The problem is another 7 kilometers upstream is the dam that provides 25% of Ecuador's power, and Ecuador is in an energy crisis. And so it helps to work for an organization whose risk tolerance involves getting shot at, because we were the first ones allowed on the plane during COVID. So we went down there and just started consulting with them. We have great collaborators down there. Pedro Barrera Crespo and Pablo Espinosa Hiran are just fantastic engineers down there. Paul Boyd, I work with Paul Boyd, and then we've had multiple agencies working on this. Amy East from the USGS, Eddie's come down with us, 4 different agencies, 30 collaborators. This is the original geologic profile. This is the current profile, and the dam is up there. And so this is an unprecedented event in the Anthropocene. Basically, we've seen evidence of this in the past, but we've never seen it happen in human history. And so when something's unprecedented, numerical models maybe aren't the thing to use. Numerical models, like AI, integrate human knowledge. This is outside of human knowledge. And so I've been working with Jeremy Sharp, who is one of the best physical modelers of our generation down at ERDIC, and we've been running physical models of some of the different alternatives that we're looking at. All right, so if you've been paying attention, I said 7 sediment scales, and we've talked about 6. And there's one more scale I want to hit. I have a hypothesis, and at this point, I have enough evidence that I think it's more than a hypothesis. All channel design projects, whether they be flood risk management, navigation, or ecosystem restoration, their number one failure mode is morphological. It's sediment transport. But that's not part of the standard curriculum. And so that's okay. We're just talking, there's not room in the curriculum for sediment transport. It doesn't hurt my feelings, but we have to fix that as a community. And so the 7th scale of sediment transport that I really care about is what I'm going to call scalable, generationally accessible tech transfer in science and communication. And when I went on that walk thinking, why did Jennifer and the team give me the award? I think, maybe it's RAS, but also what I really want to do is provide some sort of tools for hydraulic engineers to think morphologically, because it's going to matter. And so we went to the YouTubes. There's an official sediment transport YouTube channel, HEC sediment YouTube channel. And over the last 4 years, we've done a 250,000 views, and this blows my mind. Over 15,000 hours of watching. And then I stood up a RAS YouTube channel that's doing the same numbers. There's 140,000 RAS users. There's 9 of us. And so we're looking for scalable ways to build expertise. And then I'm a podcast guy. I like to listen to podcasts while I'm running. And one day I was just like, why isn't there a cool podcast in my field? And then I just decided, well, maybe you should do it. A lot of the learning that I've had in sediment transport over the years has just been conversations next to rivers. And so we're trying to replicate that. We're talking to a lot of the people that mattered to me over the years about sediment transport. And here's the best recommendation I can give you. It sounds like it might be boring, but it's not. That's about what you could ask for a sediment transport podcast. And people ask me, where do you find the guests? Well, a lot of them are my mentors. People have mentored me over the years, but there's a list I look at. It's the Einstein Award winners list. These are the people who have mattered to me, whether I've known them or not. Over the course of the past year and the future year, there's going to be a number of the Hans Albert Einstein Award winners on there, because these are the people that have mattered to me. I don't really believe in individual awards. I mean, it's physical, it's right there, like it exists, but I just don't think there are any individual awards, at least not the way I do science and engineering. I would not be who I am, and I would certainly not be receiving this award if I wasn't embedded in one of the finest teams in civil engineering, which is the HEC RAS team. And I need to recognize in particular Alex Sanchez, who studied with Wei Ming. He came on 10 years ago on the RAS team and has done a lot of the numerical work and has really done a lot of the heavy lifting in 2D sediment transport and debris flow. I also want to recognize Paul Boyd, John Shelley, and the really remarkable young generation of core sediment SMEs. In the core, we're not incentivized to write papers. We don't often get to go to conferences, so you probably don't know these people. They're remarkable. The core is in good hands when it comes to sediment. And then I just have to end with Tony Thomas, the author of HEC 6. He came and did a visiting scholar stint at HEC early in my career, and there was a time when everything I knew about sediment transport was from Tony. And the reason I didn't even notice this until I was practicing this talk, but the reason, if this is a good thing to end with, is look behind Tony on the wall. And what you'll see is the 5th ever Hans Albert Einstein Award. I would like to thank David Williams for the nomination, and the deliberation committee for this outrageous award. It's one of the great honors in my career. Thank you.